Hi everybody, I'm Mr. Folly, and this is Mr. Folly with sound. How about that? And welcome to 1.1. So I try to keep these in here. This big idea ones, this will cover all the big idea ones. I'll try and have it match up and tell you where we are with the 1.1s and 1.2s. And the U-dos help see that, and a handful of other things work with this. So we're going to start with moles and molar mass, okay? Chemistry is done in moles. A mole is a grouping of atoms, molecules, or ions we call an indiscriminate grouping of atoms, molecules, or ions, particles. This means we don't have to go, that's not an atom, it's a molecule. So we're going to call them particles for the most part. A mole is 6.02 E23 particles, which looks like this. Okay, that's lots. So that many particles make up one mole. This means particles are small. If I have a whole bunch of them, it's small. Okay. And a mole, believe it or not, this works pretty well. The groupings are about a handful. Okay, a ream of paper is 500 sheets. That's a handful. A gross of bottle rockets, 144 bottle rockets. That's a handful. Okay, even if you miss fingers, haha. Little Indiana fireworks humor for you. Formulas are listed in number of particles, so that's pretty much moles. CO2 means I have one atom of carbon and two atoms of oxygen. So this tells us the ratio of it, right? So this is the ratio. It's a 1 to 2 ratio. 1 dozen carbons to 2 dozen oxygens, or 1 mole of carbons and 2 moles of oxygen. Sorry. And that's what we're going to use most of the time. Just assume they're in there. Moles are typically converted to and from grams, as balances are easy to find and use. Molar masses are on the periodic table. So the molar masses are the decimal numbers that are on here, okay? 55.85 means there are 55.85 grams in 1 mole. 55.85 means if you have this many atoms of iron, its mass will be that much. 55.85 or 845, if you're really crazy with it, means one atom of iron would typically weigh 55.85 atomic mass units. That's a made-up unit, and we don't use it very often, but it works whenever you want to talk about one atom at a time. Okay. All right. 1.1, determine the molar mass in grams per mole of the following substances. So I've got to look at my periodic table. So in my periodic table, I got to look up copper. Okay. So copper on my periodic table is, well, let me do this. Oops. Okay, so I'm going to show you how to find on the periodic table. Oops. So let's take a look at copper. Copper is 63.55 and chlorine is 35.45. So that means I have 1 copper and I have 2 times 35.45. And that's molar mass. So this will tell me how much a mole, remember 6.02 times 10 to the 23rd particles. 63.55 plus quantity 2 times 35.45. Closed quantity is 134.45. And then the units we want to use for that, it says in grams per mole. Another unit I asked for grams per mole would be AMU. Okay. Magnesium nitrate. So for magnesium nitrate, I have 1 magnesium, I have 2 nitrogens, and I have 2 times 3, 6 oxygens. So I'm going to look at magnesium, 24.3, nitrogen, 14.01, oxygen, 16.00. So 24.3 plus 2 times 14.01 plus 6 times 16. And notice where we pull 2 decimal places on each of these. I said 24.31. Didn't show up. So I have 24, whoops. I have 24.31 plus quantity 2 times 14.01, close quantity, plus quantity 6 times 16, close quantity. I get 148.33 grams per mole. Okay, so there's a new type of compound you haven't seen before. Oh no! These are called hydrates. What a hydrate is it means I've got water clustered to it. So if this is my molecule, what happens is I get water. Water. In this case, I have 5 waters. I'm running out of places to do it, but I have 5 waters stuck into it. Okay, so it is a new compound. compared to CuSO4. Okay, so CuSO4.5H2O is not the same as CuSO4 all by itself. Okay, kind of like bread is not the same whether it's stale or if it's fresh, right? Oh, I think my dog's gonna bark at me. Okay, so this is just, I'm going to find copper sulfate and then add 5 waters. Say hi, Penny. Say hi. Okay, she said hi. So copper is 63 point, I forgot. Copper is 63.55 plus 1 sulfur, which is 32.07, plus 4 oxygens, 4 times 16, plus, now I have memorized, and you will too, water is 18.02. So you use that number a lot. Let's add all those up. 63.55 plus 32.07 plus quantity 4 times 16, close quantity, plus quantity 5 times 18.02, close quantity. I get 249.72 grams per mole. So now, new and different things. How many moles are in 3 grams of iron? So we're going to show this work this way, and we're going to do it this way, because as it gets longer, it's going to get meaner, okay? So I have 3 grams of iron. What I'm going to do is I'm going to make a fraction and multiply it by 1, essentially. So from the periodic table, I know that 55.85 grams equals 1 mole of iron. 55.85 grams of iron equals 1 mole of iron. So I'm multiplying by 1, so then I take 3 divided by 55.85. I can multiply it by 1, 3 divided by 55.85. I saw I fat fingered it. Equals 0.0537 moles of Fe. Now I can multiply by 1 if I want to, but when you multiply or divide by 1, it doesn't do anything at all. It's like kissing your sister. So, how many grams are in 2.51 moles of F2? 2.51 moles of F2, and I want to go into grams, so I need an equivalency. So 1 mole of F2 equals, let's look at the periodic table, and we'll always have this periodic table, so we can always look. F2, F is 19, so double 19 is 38. So 2.5 times 38 is 95. All right. Now, part 2. Mass spectroscopy. Ooh, doggies. So atoms are made of protons, neutrons, and electrons. There's a lot of stuff that's going on here, okay? Protons determine the identity. They're involved in mass and charge, but for now, just know that's identity. Neutrons determine nuclear stability and mass, and electrons determine charge. So right now we're focusing on charge, we're focusing on identity, okay? So let's look at that periodic table again. Hey, guess what you're going to get in class tomorrow if you didn't look it up and print it already? A periodic table. So let's look at our friend boron. Our friend boron is right here. Yours, I think, has names on it. So boron is right here. Its symbol is B. Boom. Atomic number, 5, the whole number, 5. Atomic number is the number of protons. You got that? Determines the identity. That's why it's called the atomic number. Okay? So these will always be equal to each other. Number of electrons is going to be the same as protons. So these are kind of the same. I'll show you when it's not in a minute. Nuclear notation is going to be boron, and I've got to have the mass on top, and I got to have protons on the bottom. So my mass is, okay, so we've got to get back to this mass part, okay? So mass is protons plus neutrons. So my mass for boron is, well, this says my mass number is 11, right? So notice how if my mass number is 11, I have 6 neutrons plus 5 protons. And my number of protons down here is 5. I could also use atomic number for that if I wanted to. Hyphen notation, which nobody calls it that. That's okay. Boron 11. Notice how this right here is the mass. Okay, so here, let's take a look at this. So I know I have 8 electrons, 5 neutrons. Okay, so it's still going to be boron. B is going to be boron always. Atomic number, always, remember that's the number of protons. That tells you the identity, so that's pretty good. Now remember, my mass number is protons plus neutrons. 5 plus 5 is 10. Hey, I'm pretty good at that now. Nuclear notation, I call it isotopic notation a lot too, is going to be mass on top, 10, protons on the bottom, 5, still going to be boron. Okay. Okay. Hyphen notation, this one's a little bit different. Boron dash 10, because the mass is a little different. Okay. Let's take a look at this one. 36 is the atomic number. Oh, make it a little smaller. 36, the atomic number, mass is 84. 36 is the atomic number. Dun, 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 dun. Krypton has a 36 for a mass. So element name is krypton. Symbol is Kr. Okay, atomic number is the same as protons, 36. Mass number is 84. So 84 minus 36 is going to be my number of neutrons, which I admit right now, it's been a long week. I'm taking that to the calculator and going to 48. And my number of electrons is going to equal protons unless there's some reason to think that it's not that, which means it tells you a charge. Number of electrons, same as protons, 36. Nuclear notation, krypton, mass is 84, 36 protons. Okay, hyphen notation, krypton dash mass 84. All right, atoms of the same type may vary. They have the same properties except for nuclear stability and mass. Okay, so people in the same family may vary. They have the same properties except for stability. Hey, I'm the crazy brother. I'm the black sheep of the family. And mass, me, I tend to like to eat more than my brother. So I'm the chubby one, and I'm unstable. So still follies, but there it's a little different, but still very much the same. Not the biggest difference, right? It doesn't matter. I'm not that different of a person just because I'm chubby. A little bit more different if I'm a little bit less stable. That's all it's it. Isotopes are the same type of atom but have a different mass. My neighborhood has 2 dogs that look like my dog. Penny, you heard her bark before, and Fat Penny. Both are the same type of dog. Both poop in the old man's yard. Both bark at the Amazon driver. But Fat Penny, guess what? Is carrying a little extra poundage. And that's it. That's the only difference. Okay? So one way to show this is with mass spectrum data. Mass spectrum is always called mass spec, determines the number of isotopes and the abundance of those isotopes. Okay? Do you see how there's 3 peaks here? 1, 2, 3 peaks. The number of peaks tell you how many isotopes. There's 3. Okay, do you see how chlorine has 2 peaks? 2 isotopes. The relative height tells you the abundance. This is tall. These are small. And they're equal. Okay. Oops, my tall didn't show up there. So tall means there's more of it. It can't be 100, right? So this is the relative intensity. Okay. It can't be 132%. You can't have 132% of something. So the relative intensity, this is 100 and this is 10. That will tell you a different bit. Okay. The bottom numbers in blue show you the percentage abundances. The bottom numbers in blue. This is my percent. 78, 10, and 11. I said they were the same, but the intensity is 112, 13.94. Okay. Over here, my percentages, 75.76, 24.24. See how those add up to 100? All right. Top number shows intensity. I like chlorine the best, so it is 100. It's the most common. And 37 chlorine, I like 1/3 as much. This shows the 37 is 1/3 as high. So if I have 1/3, 1/3, 1/3, that's 75. Okay. So looking at this, 1/3, 1/3, another third. See how you can tell this number right here is indicating a third. So that means it's 75% and 25%. All right. An element is composed of 3 stable isotopes, A1, A2, and A3. Isotope A is found 15% of the time, isotope 2 is found 65% of the time, and isotope 3 is found 20% of the time. The atomic mass of these things are 50, 52, and 53. Draw a mass spectrum. Okay, so percent abundance. Notice how this is just percent abundance. So A1 is 15% of the time, and A1 is 50. So at 50, and it's going to be 15% of the time. Okay. A2 is found 65% of the time, and it weighs 52. Right, so 52. And then 53 was 20% of the time. 53 is 20% of the time. That's it. Identify the element from the following. Okay, relative abundance. So looking at this, do you see how this is mostly 90-ish, right? So if I were to guess the average of this, I'm guessing this guy to weigh about, see how these guys kind of drag it over, 91-ish for its average. So let's cruise the periodic table and see what weighs about 91. Masses are down here. What weighs about 91? So I've got zirconium and niobium. Let's see if any of those are choices. Zirconium, and niobium. Okay, so niobium, where'd you go, niobium, is 93. You think the average is 93? There's not enough to pull it over there. It's not going to be niobium. That's not 93-ish. Zirconium has the preponderance of the abundance. Average atomic mass. Atoms are really small, so we always have more than 1 million atoms at a time. So the mass is the average, and that's the mass we expect to use. So the average atomic mass formula is mass 1 times percentage 1, mass 2 times percentage 2 for each one that you have. Remember, percentages have to be done in decimal form. So we'll do one of these, and then we'll call it a quit. What is the atomic mass of hafnium? Which, by the way, is HF. If out of every 100 atoms, 5 out of every 100, that's 5%. Man, I'm not writing very well today. Let's see what I can do here. 5%. Man, it's not right. It doesn't like me today. All right, slower. 0.05 of hafnium. Okay, you're getting me here. So I'm going to have to put this on a new one. 0.5 have a mass of 176, 19 have a mass of 177, and 27 have a mass. So I'm going to flip back and forth. 5%, right? So that's going to be 0.05 have a mass of 176. Plus, then I had, what percentage? Then I have 19 out of 100. 19% is 177. Point. Man, oh man, oh man. Let's see if maybe I change this. 0.19 are 177 plus then I have 27 is 178. It's going to be 27%. Point. Oh man, you can tell it's kind of mad here. You know what? I'm going to give up on this one because it's not going to let me write. Let's take a look at it. So then we're going to just look at this part right here. Percentage 1, 5. Percentage 2, 19. Percentage 3, 27. Percentage 4, 14. Percentage 5, 35. Right? Now, if I want to have that mass, right, my mass is going to be 176, 177, 178, 179, 180. I'm going to do that math. I don't know why my pen won't work, but I will say this. It was a blessing to us because it gets us out of touch earlier. And to that, I will say, toodles.